All right, let's start with our second talk for the afternoon. Kyoung Seog Lee, he's going to tell us about Motivic aspects of complex analytic geometry.
Thank you very much. So, yeah, thank you very much for the introduction. And I would like to thanks to the organizer for inviting me here.
Microphone. Yeah. Oh, turn it on.
Yeah. Right.
Hello.
Yeah, thank you very much for the invitation again. And as Laurent and Ernesto mentioned, this is based on a joint work with Ludmil and Ernesto and Laurent. So, yeah, there will be some overlap with what Laurent and Ernesto told. Yeah, let me start. So we will basically work over C. Everything is over C today. And so let me first recall basic fundamental theorem of the ring. So it's a theorem by the ring. So saying that when X is an algebraic variety C, and there is functorial mixed art structure on cohomology of X. We prove this, and then using this, one can actually so then if we define Gross-Ring of variety, let me just repeat the definition of Gross-Ring of variety. So the Gross-Ring ring of variety is defined in this way. The ring of algebraic variety is a free abelian group generated by isomorphism class of algebraic variety, where X is algebraic variety, and I divide this by relation where this class of X, isomorphism class of X is equivalent to X complement G plus the class of G, where G is closed algebraic subvariety. So if I give relation in this way, then I can define this Gross-Ring ring of varieties, and then the rings resolve, and actually I give a ring structure, so x1 class of x1 times class of x2 is defined class of x1 times x2. And if I define a ring structure in this way, then of course this becomes a ring, and the corollary of the ring's result, the ring's construction of mixed art structure plus Mayer-Beatrice sequence actually gives that there is a ring homomorphism from Gross-Ring ring of varieties, algebraic varieties, to this GUV, where when X is a smooth projective variety, this maps to this first polynomial -1 to the J H P Q X, then U to the P and B to the Q. And actually, in this case, firstly, plus Q, and then this become a well-defined ring homomorphism. So the basic question I would like to ask is, can we extend this picture to general to complex analytic varieties. Analytic varieties.
Compact.
Yeah, but, I mean, indeed, some complex analytic varieties. I will say more in color. Okay, yeah. I mean, yeah, Bayesian model will be compact. Compact, there will be no, yeah, Bayesian model will be compact, but we will also consider open sub-varieties, compact, complex, uniforms.
Yeah, but the first definition, those were compact varieties.
This one, actually, this can be understood as kind of generator of the string. So I just send this generator, this generator to somewhere, and this actually defines the ring homomorphism. So actually, yeah, actually there can be non-compact algebraic variety, but there is mixed up structure on this. I consider the compactly support cohomology, and there's a canonical mixed up structure. And using this canonical mixed up structure, I can still send this to somewhere. So anyway, this is generator. That's the very question is. So this is generator. And actually, when I know where this goes, then actually this will determine the ring homomorphism, entire ring homomorphism. Thank you very much. And the whole point is, can he anyway extend this to, as you mentioned, non-compact analytic varieties?
You can extend the definition.
Extend the definition. Well, okay, let me say it this way. So, what I mean is that maybe what you ask is, can he say something like, cross-ending ring of complex analytic varieties is like, something like pre-Abelian group generated by this class where X is just general complex analytic variety and taking quotient by certain relation where X is same as X complement G plus G, where G is closed analytic variety units. And maybe the natural question is, okay, can he somehow extend or ring homomorphism from this complex analytic varieties to some G, U, V, something like this? And actually, what we can say is this is impossible. Indeed. Let me explain why. But the short answer is, can he somehow naturally extend, construct a ring homomorphism from this just defined ring to by sending X to HPQ, X U to the P, U to the Q, maybe minus 1 to K. And the answer is no. Let me explain why. So indeed, the mixed up structure, the basic reason why this is impossible is, let me say remark. So the mixed up structure when X is complex analytic variety, so let me assume, sorry, let me say it this way. Let X be a complex algebraic variety, then Y be also complex algebraic variety. And suppose that X and Y are analytically isomorphic. Then Berlin, actually what Berlin tells us is there's canonical mixed dot structure. So this has mixed dot structure constructed by Ludmil, and there's mixed dot structure here. But actually, this mixed dot structure doesn't need to be the same. So this doesn't need to be same in general. So in other words, this mixed dot structure, the functorial mixed dot structure on X actually depends on underlying algebraic structure. So I mean, this analytic structure itself doesn't determine, mixed dot structure. So one example we know is something like this. So let me consider elliptical. Then by almost definition of elliptical, I have canonical extension of line bundle by line bundle. So because x1 is C. And then I can projectivize this vector bundle over C, over E, and this double bundle actually gives a section. This canonical double bundle gives a section, and then I consider U, which is complement of image of this section. Then one can actually show that. Anyway, then this is actually T vector bundle on E, and we can consider universal covering of E and this U, and if you consider this pullback of, if you consider this universal covering, and if pullback is U, then actually this becomes C times C, because this is C vector bundle of C. And then this covering action G2 actually leads to here, and actually you can show that via this argument, you can show that U is analytically analytically isomorphic to isomorphic to C star times C star. But this C star times C star has natural compactification to P1 times P1. And well, there are two natural ways to compactify these two U and this analytic variety. And one can show that the mixed dot structure, let me say C star times C star is algebraic variety embedded in here, and let U be the complement of this section, and then which I think by itself, one can prove that the mixed dot structure on U is different from mixed dot structure twice. Mixed dot structure of C star times C star. So I mean the underlying, mixed dot the mixed dot structure of cohomology actually depends on this algebraic structure. So in this way, you can see that actually if we just naively define corresponding ring of complex analytic varieties, and if we just define this UV by sending generator to some L, and this actually does not work well. I mean, is not. I think this is not a ring move. So if we want to extend this picture, we need to do something. So to limit this thing. So, but before going there, is there any question?
There's a comment that order characteristic.
Yeah, we're looking at the extent, right. But touch is very, yeah.
Imagine order characteristics of various twisted versions might also.
Yeah, right. Yeah, right, that's right. So, well, this is a little, I mean, yeah, Euler characteristic and homology to some extent, but this is a little more subtle structure, depending on algebraic structure. All right. Thank you. Any further question? So then, in order to remain this, I need notions of called the minimal structure. So let me briefly recall structure. So on O minimal structure is so collection of collection R which is N where R is non-negative integer of subsets of Rn is called structure if it satisfies the following conditions.
Oh, minimals, right? You said, but didn't write oh minimal or no?
I now define structure,
Oh,
and then I will define what is O minimal structure. Thank you. Let me first define what is structure. So a structure is collection of subsets of Rn satisfying the following conditions. First is Rn forms a Boolean algebra of subsets of Rn, which means just it's closed on the finite intersection and finite union and taking complement. This is first property. And well, and if A belongs to Rn, then A times R. So this means A is a certain subset in Rn. So and then this implies that A times R belongs to Rn plus 1, and R times A also belongs to Rn plus 1. And third condition is now this xi equal to xj is also in Rn. So where xi and xj are just i's coordinate and j's coordinate of Rn for every one I, j, n. And the fourth condition, this is highly non-trivial condition, but if A belongs to Rn plus 1, then its projection to Rn belongs to Rn, where this phi is a linear projection from Rn plus 1 to Rn. And if a collection of subsets of Rn satisfies this property, then I will say this is to be structure.
what does 3 mean?
3. I mean this is that where the i's coordinate is same as j's coordinate. The value of i's coordinate is same as j's coordinate. Something like, well, it's something like x equal y in R2. So it's this subset. And I mean this condition says that this set is also in here. Yeah, let me give one example. So let me
No if or it's not quantified. Oh, for all
So for all I and j, where I and j belongs to is from 1 to n, so I consider i's coordinate, and I consider j's coordinate, and I consider the set in, so this is set in our subset in Rn, where i's coordinate, value of i's coordinate is the same as j's coordinate. This is in R2, it's this guy. And then, I mean, this says that this type of set belongs to Rn. But to be, yeah, I mean, it means anyway that some special sets are belongs to. And actually, the most important condition, in my opinion, is the first one and the fourth one. And well, I mean, also define what is homogeneous structure and give an example. So the fifth example is a structure is homogeneous structure if well, the fifth condition, if fifth condition, so for any x, this set belongs to R1, and this xy 2, where x equal to y is 2. And again, the most important condition is the sixth one. Actually, this one-dimensional, I mean, this one-dimensional set is consists of finite union of open intervals and points. So let me give an example. So the example is like this. So I consider set given by, I mean, I consider, so zero locus of finitely many polynomials, and also set given by finitely many inequality, where these fi and gj are polynomials. Fi and gj are polynomials. So then I consider the Boolean algebra generated by this subset. This will be called the semi-algebraic set. And then by fundamental theorem of Tarski and Seidenberg says that when this type of set will be called semi-algebraic, and fundamental theorem of Tarski and Seidenberg says that the image of semi-algebraic set is still semi-algebraic. So if I just linear project semi-algebraic set, then the image is still defined using finite number of polynomials, real polynomials, a finite number of equality given by linear polynomials, and finite number of inequality given by linear polynomials. This is called, this is theorem of Tarski and Seidenberg. And when you see that,
statement using the word semi-algebraic set and zero minimum sets. What's the statement?
Which is the statement. So
Is the statement semi-algebraic sets equals zero minimum sets?
Yeah, semi-algebraic set form homogeneous structure. That's the
That is no minimum. That's an example.
that's the example.
Okay.
Yeah. So thank you very much. So if I consider all semi-algebraic set, maybe Boolean algebra generated by semi-algebraic set in Rn, then in Rn, let me say that. So in Rn, then this will give homogeneous structure. Or semi-algebraic, the homogeneous structure of the semi-algebraic sets. Yeah. And well, let me finish this sentence. So if you consider R1, then this is a Boolean algebra generated by obtaining finitely many zero polynomials and finitely many inequality. And when you see that any polynomial in R1, the inequality is given by, if I give an inequality, then this set is given by this type of thing, and the equality gives finite number of points. So you actually see that you actually can see that this R1 actually consists of finite union of open intervals and points. So anyway, this is the example of O-minimal structure, on O-minimal structure. And actually, you can change this. This is one example of O-minimal structure. But actually, you can change this. You can give another O-minimal structure by considering some other functions. So if you give more general functions, then you can create another function. But it is not obvious that which function will give an homogeneous. It's actually highly non-trivial task. I mean, if you consider arbitrary function, then and consider this type of set, then this will not give an homogeneous structure. So you need to choose very specific function, and then if you are lucky, this will give an homogeneous structure. So there are several well-known homogeneous structure business. So for the semi-homogeneous structure of semi-algebraic set, homogeneous and the homogeneous structure, or if you consider not only polynomial but also real exponential function, then this will give a homogeneous structure. This is proven by Wilkie. And if you consider less strict analytic function, so for certain analytic function, and then this will give also homogeneous structure, and you can also consider homogeneous structure generated by these two, and there are four typical homogeneous structure which we will use. But actually, we will focus on this as homogeneous structure. So. Okay. Any question? So then first we need to and if you are given a homogeneous structure, then this is a homogeneous structure, then you can consider a definable set and definable function. So a set in Rn is definable if A belongs to this Rn. So yeah, Rn is, once again, this is collection of certain special subsets in Rn, and if this guy belongs to this collection, then I will say this is definable. And a function f from A to B is definable if its graph is definable. So if this is Rn, this Rn, then if this is definable set in Rn plus 1, then I will say a function is definable. So since we are, given what we decide what function and why this function is definable and what set is definable, we can do geometry. So I can actually do kind of complex analysis using this thing. So there is a theorem by Lupercio and Stashchenko saying that let X be a complex manifold. Then they proved that this is always definable. Definable. Well, RAN and its extension. So
Wait.
this
X is definable, what sense?
yeah, thank you. Let me explain. So yeah, thank you very much. Let me explain. So X is X is compact complex manifold. So for any X, any point I can define this chart. I can give this open chart from this open set to the end. And actually, I can identify, of course, the Cn to be R2n. And I have another chart giving, sorry, hexons. So I can give another chart, and this gives another map from here to Ij, and this Z. Where Ui and Uj. So this means that X can be covered by finite union of open chart. And of course, this open chart gives me a map from this to Cn, which is equal to n, and the image is defined over open subset here. And in the intersection, this is of course holomorphic biholomorphic function, since this is complex manifold. But this is not only biholomorphic but also definable. So I can always, but this means that I can always find a finite open chart, finite open covering of my complex manifold, and the image here is defined over open set, Cn, and these transition functions are all definable, biholomorphic and definable. So, yeah. Anyway, so this theorem actually
means that real variable functions are definable.
Yeah, exactly. So I only define definable function on real variable functions, and I regard this transition function as a real function. So this is R.
It's definable relative to some zero minimal structure on Rn, R2n.
Yeah, right.
That's what you.
Yeah, exactly. Thank you. Yeah, sorry, I was disrupting here. Any question? So anyway, this Thomas says that.
Is every compact complex manifold satisfy this? Oh, that's the theorem.
Yeah, that's the theorem. So I mean, yeah. So they prove that every complex manifold is defined and can be given a definable structure.
Wow.
So then I consider, I mean,
Is this sort of arbitrary or minimal structure?
No.
It's about the right.
Sorry, it's definable over this minimal structure. The minimal structure given by elastic analytic. Thank you. So actually, from now on, my minimal structure is this guy, OH expansion. So expansion means I just consider more that. So I mean, when theorem holds for here, then it's automatically holds for
it's
expansion.
This is semi-analytic good work, right?
So it's actually kind of an analogy of sub-analytic instead of sub-analytic. Yeah. It's actually, I mean, to be precise, it's omega structure generated by elastic analytic function. But this is kind of analogy of sub-analytic functions.
How does that differ from semi-analytic?
Semi-analytic is, sub-analytic is image of, it's set generated by. I mean, we need this category to be closed on the projection.
Yeah.
So I mean, so I need sub-analytic sets. I mean, to make this into.
I thought Tarski's theorem showed that was true, semi-algebraic.
So it's a semi-algebraic. So
Oh,
sorry, this guy is restricted
okay,
analytic
right.
function, which
Okay.
is analytic function restricted on compact parts. Thank you. Okay, so anyway, then I can consider something like this. So I consider this cross and the ring of definable analytic, functions. So okay, let me go with this. Let me say that. So I consider that I mean so by previous theorem, whenever I have complex manifold, this can be given a definable structure. Then I consider Zariski locally closed subset in a compact complex manifold, which is definable. So I will say this to be compact definably, compact definable analytic spaces. Then
Well, what is the word Zariski?
Zariski means I consider holomorphic function. I mean locally. I mean this is given by local holomorphic zero set of holomorphic function. I mean intersection of zero locus. So this is let me say this. So Zariski means this is closed analytic of variety. I mean this zero locus loop. Wow. Zariski means, this is, I consider, when I have this one, then I consider this analytics of variety. So variety locally given by some general functions, general locus of certain holomorphic functions. And here it should be locally, definably locally given by definable holomorphic analytic function, and then I consider this then this is closed set, and the locally closed is just this complement of, and then I consider this Zariski open, which is complement of the set of this type, and locally closed just means that intersection of this open and closed given by this Zariski, it's given by this function, local definable holomorphic function. Then I consider this definably compactifiable analytic spaces. Then I define a Grothendieck ring of definable analytic space. So this is pre-Abelian group generated by definably compactifiable analytic spaces. Take out this relation where this isomorphism class is x complement g plus g, and well, this g is again this closed definable analytic subset. Definable closed analytic subset in X. Then
You drop the product. You drop the product.
I will consider product too. So this is actually
Joey's mean both.
yeah, exactly. I consider only group structure, but I don't say ring structure, but ring structure is also there. Because this ring structure can be given by x1, x2 is x1, x1. just the cross product. Then theorem I wanna mention is then is again trying to work with Ludmil and Sag and Ernesto and Laurent. So if I consider this definable space, then actually sorry, I also forgot to mention one thing. So I mean in Carol case, there are these Hodge polynomials were defined, but when X is general compact complex manifold, then there are actually three types of cohomology, which is Apley and POSTECH and Dolbo. So I mean there can be more, but I mean these are three typical cohomology theory. And
What is A and B, C?
Sorry, this is Apley cohomology. This is given by sorry. Just 1 second. This is given by this column, this model by image of this guy, and POSTECH
Okay.
is
Butcher.
POSTECH and Dolbo.
Okay.
Yeah. So there are three. I mean, I don't know. There can be more, but there are very natural cohomology theory, and these cohomology theory are all coincide when I consider Kähler manifold or manifold satisfying this dilemma. But in general, it doesn't need to be same. But in our case, we can prove that. I mean, but anyway, we can prove that there is a well-defined ring homomorphism. There exists. There's the ring homomorphism from this cross-ending ring of defined over analytic space to GUV, which sends this X. This is a compact complex manifold to this HPQ, and it's HPQ X U to the P HPQ. And this becomes a ring homomorphism.
For each of these three theories.
Yeah, each of these three theories. Actually, any theory, any cohomology theory satisfying Blow formula and product formula is false. So because thank you. Let me explain how we actually prove this. So the idea of proof is we somehow prove the Bittner type theorem. So which means that it goes back to this algebraic geometry case. So if I consider the ring of algebraic variety, then actually one can show that this guy is generated by it's a pre-Abelian group generated by smooth projective varieties, quotient relation, and this relation is given by this way. So I consider smooth projective sub-variety, and I blow up. And then I consider its exceptional divisor. And in this case, everything's are projective. So then I give this relation rho of x minus e is Laurent. So I mean the cross-ending ring of variety actually originally defined by originally the definition was x is equivalent to x minus g plus g. But actually one can prove that this cross-ending ring of variety satisfies have Bittner type presentation, which means that this guy is generated by smooth projective variety without this relation. And again, ring structure is given by product. And we actually proved the same thing. So if I consider this definable, and this is generated by X, where X is compact complex manifold. and given by the law of relation, which is exactly this one. So actually, any cohomology theory satisfying this Grover formula and product formula, which is just Kines formula, and one can show that this actually gives this ring homomorphism called Motivic measure. Yeah. So I mean, yeah, there can be many other cohomology theory which gives the Motivic measure, but at the moment, I think.
You're using resolution singularity.
Yeah.
The analytic space.
Yeah, we use resolution of singularity. Resolution of singularity and factorization. So, yeah. Proof is more or less, I mean, adopting algebraic geometry case to analytic case. Thank you. Yeah, and actually, please recall that, I mean, this stuff actually comes from, this Motivic measure actually originally motivated by theorem of the mean to prove that this, for every algebraic variety, this has canonical mixed-up structure. Actually, one can show that. So, okay, definition and say. So, a complex manifold, complex manifold is of Pushki type C. See if it is meromorphic, to a compact Kähler manifold. And the Kähler manifold, satisfies all these nice properties. So then we can actually construct similar things. So so then if I consider theorem, say, so when X is locally closed, definable, locally closed subset in manifold of Pushki type C, then we can actually prove that cohomology has canonical mixed-up structure. So, Pontoria, maybe we can say Pontoria. I mean, Pontoria or canonical. So, actually the construction is more or less already done by Laurent. So actually, when you read Laurent's paper, he actually suggests how to construct a mixed structure by compactifying your manifold into compactifying. First, if you see Laurent's paper, he constructs a mixed structure in this way. So first, whenever I have an algebraic variety, I can embed this into its compactification by Narada compactification, and then I can do resolution of singularity to make this into algebraic variety. That's resolution of singularity, and then I can consider this X is embedded into N, and this complement is normal crossing inversion. And then using this normal crossing divisor, he constructs a mixed structure. So, the construction part is actually more or less already done by Laurent. What we can prove is this is actually canonical or Pontoria using this definable structure. So, actually, this definable structure is key because, for example, the previous example of mine, so if you see this view and this times this term, the key point here is this is analytically isomorphism, but this is not definable. Actually, this underlying definable structure is kind of key to distinguish these two mixed-out structure. Okay. So yeah, this is a
That's your old example.
pardon?
That's your example from before.
Yeah, that's my example before. So this is thank you. This is P, this vector bundle minus this section of elliptical, and this is analytically isomorphic to sister times sister, but this is not definably isomorphic to definably biholomorphic to this guy. Yeah. Sorry. So anyway, so this, so actually this definable structure is actually somewhat key. We believe this definable structure is kind of key to extend this mixed-out structure. Otherwise, it's not well defined. So yeah, that's the thing. And let me mention one last thing and finish. So there is a theorem by Ominimal Cho theorem. So actually, this is originally proved by Joe and Skashenko, but also we run this version by Ko and Bobo, Shinoman. Say that, when X is an algebraic space, and if this is a closed definable complex analytic subspace, then can actually prove that this actually comes from algebraic variety. This is algebraic variety, the algebraic space, subspace. So then this actually somewhat show that if I consider this Rosen ring of my algebraic variety, then there is canonical map from here to this Rosen ring of definable, compactifiable, definable analytic space, and actually you can show that this is embedding. So what we can say is, if I consider this, this Rosen ring of definable analytic space, then there is a Rosen ring of actually algebraic variety, and then we can also consider complex analytic space of Kuchiki class C. I can consider this complex analytic space of Kuchiki class C, and actually this. And the Laurent theorem imply that if I consider an LBM manifold, so if I consider LBM manifold, then actually after some stabilization, sorry, let me say this is already it's zero. Sorry, interesting. So then anyway, I already discussed that this from here I have a ring homomorphism from here to G to V, and which goes to there are several, this Dolbo and this Lee and this Woodchon. And also I can send this to here, and this is drum. And can actually think, the difference between two ring homomorphism is not a ring homomorphism, of course, but we can consider, if I consider the kernel, for example, if I consider the variety where is a class where, for example, this Dorbo is same as, let me say this, right? It's the same as Ron, which roughly saying that this is the hot decomposition is true, or this, if I consider add all this hot number, this becomes steady number. So then this is not obviously subring, but actually this is here subgroup, and actually this is actually submodule. This is I0 algebraic submodule. So Laurent theorem someone says that. So I mean it's kind of here where chi term is same as chi.
Raise it. Look.
Sorry. Sorry. This little. Is it okay now? Yeah. Chi term is same as chi. And Laurent theorem someone implies the theorem Laurent mentioned, but it's interesting in this sense because I have start from this Airbnb manifold, and then I do some stabilization. Then actually this goes to here. So in some sense, we think a question is called question of conjecture questions. Okay, because I mean, can we find a stabilization, whatever it means, process to make my M for any compact complex manifold to get into where this Dorbo is the same as true. I think Laurent's, I mean, the talk gives this example that for some Airbnb manifold, you can always do stabilization and then it's actually get into this class. And I think, well, this is interesting question if we can do this in general. We think maybe some kind of road transformation can enable us to do this, but it's still early stage. So let me just leave it as a question. And let me finish. Thank you very much.